Okay, so what we've been doing is going through the book, and Ku at that point in time there hadn't been a lot of nanocellulose stuff done yet. So what we're going to do here is we're going to talk about nanocellulose, which we haven't talked about at all. We're going to look at different little things to it. I have a couple of good review articles, and then I have a few kind of interesting papers. And so this is in two parts. I probably won't get all the way through this today, but there's a second part already posted, which I'll finish up next time. Okay. Oh, but before I do that, I want to do this. I want to go over, let's see, where is it? Critical review. Okay. So I'm assigning you a critical review today. We'll start doing these presentations next week. So today is Tuesday, I hope. So we're going to be doing them starting on Tuesday and Thursday of next week. Right there, you have about 15 minutes, 20 minutes max, okay? Huh?
Delay it a little bit because we have a lot of things.
Okay. This week? Okay, do you want to like start them on Thursday next week? That's fine with me. Okay, so starting on Thursday next week, we'll start signing up for that. You are to find a good paper of your choice on nanocomposites. By good paper, it means, decent number of citations, it's something, don't get a review. You don't want a review. You want a single paper where they're trying to do something, okay? And you have to email me a copy of it so I can read it ahead of time. So then you got to read it and make a PowerPoint presentation based on this thing. And then on this page, or on the thesis page, do the MLA format for the actual reference you're using, okay? So this is a little different than what we did before. I want you to produce a thesis statement of what the authors wanted to do, okay? So you can usually find it in the introduction. It's usually in the last paragraph of the introduction, but you're going to have to reword it because our thesis statement has to be a little, I gave two good examples, a bad example and a good example of a thesis statement. What are they trying to prove? What problem are they trying to solve? Okay, so it might be as simple as, past experiments in nanocrystalline cellulose showed only lower loading levels. We attempted higher loading levels to see if we could maximize our gains. Something like that, so that would be our thesis statement. And you have to clearly state that thesis statement on here. Then what nanomaterials were used, why they use it, what processes they use, kind of the overall of what they're doing. And then this one's a little different. Well, I mean, processing, kind of what processing variables do they use? Do they have a table of the results or something like that? That would be a good thing to use there. But now this one is the one that's going to, you're going to have to work out it. Okay, so with every figure in your paper, you need to have a slide for it, and you need to tell me what the author is demonstrating. What the author is demonstrating. It's like, you don't say, oh, this is a wide angle X-ray scattering, and we show, no order. Don't do that. What the author is doing by using this figure is they're telling you that they got good dispersion on all their loadings. This was their highest loading. Even on their highest loading at 15%, they still got good dispersion. They still got full exfoliation. Okay, so this is demonstrating that their processing method produced a well-dispersed composite at all loading levels. It's probably not going to be this. Okay, so this is just, this is probably the first figure proving that their composite was really good. And then they're going to go to their next figure, which is their, and what is the author trying to say? What data is he trying to convey? And did he convey that data correctly? Did they convey that data correctly? Now, we've seen some papers where we're looking at them, I wouldn't draw that conclusion. And so that's where you have to ask, what are they really trying to say? Okay, so it's a little different than just talking about the paper and what they saw. What are they trying to say with each and every one of their figures?
Each mean for like their data, right? Not like if they have like a diagram of
Correct.
right? So just their figures.
So and for things like, you could have SEM showing that they did have tactoids or didn't have tactoids, and draw attention to the fact that there were not.
Yes. So there would be a lot of figures, so it would be very difficult to complete them all. So we have to stick to it, right?
At least 5. At least 5, because they should be telling, and preferably showing different data points, like, so look, we improved the properties, but now our fracture sucks. You know, that kind of thing. What are they trying to demonstrate? Because usually some people will just test for the one thing they want. Fracture improvements. It improved. Okay, and they don't test anything else. But if they test, you know, try to get them and see if you can weave it into their story of, we tried this, it was okay, but then we did this and it was better. You know, what were they thinking by adding that next piece of information? Okay, it's not just that, oh, I did X-ray because we have X-ray. It's like, I did X-ray to prove that I had started with a good material. Okay, so that's, you're looking at it from a critical point of view. You're not looking at it as an information point of view. You have to get into the author's head. The reason we're doing this is that when you should be writing papers now. It's hard to start writing a paper, right? And sometimes you just have to throw out a thesis statement and start saying, what do I want to convey to my people? Is there a figure for that? Does that figure convey that information correctly? Okay, that's how I build a paper, because I like actually all figures at first, and then I build the words around it. Because the writing part is the part I didn't like. Figures part I love. So that's the one way I do it. So that's why you start with your thesis statement. What am I trying to prove? And then how each and every piece of information, or at least 5 pieces of information from there, either go with their thesis or goes against their thesis. And whether or not it was correctly analyzed. Okay, so like this, we would say, you know, that's really well disposed. That is correctly analyzed. All right, and then a summary of results. Did the author accomplish their thesis? Okay, and no is an okay answer here. You know, my thesis was I wanted to do this, but we found that this property changed way more than that property, so we actually found a synergistic effect, but we found something else. You know, so you have to dig into their thesis, come back to their thesis statement and say, did they accomplish their task? Okay. Were there changes in the polymer system relevant and impactful? Okay, were you just moving the needle 1 more percentage point up? Just trying to push that, you know, I know serial authors at some of the universities where it's like 1% paper, 2% paper, 3% paper, 4% paper, and they're using all the same data. They've only added 1 thing. So is it relevant and is it impactful? That's why I don't want reviews. I want an actual paper with an actual thesis statement.
And so if the paper actually achieve what they wanted to, then they don't have any other effect.
Well, no, I mean, they can achieve their goal, but still not have a meaningful change.
They might have additional confidence. Can you talk about that?
No, we want to look at a paper as a whole. And we don't want to like just continue to, you know, like see all their follow-on work. Because the next thing we're going to talk about is what's missing, which might be covered in their follow-on work. But we want to know what's missing, what test or process or material selection did they not do? You know, did they do, you know, 5, 10, and 20? What happened to 15? 15 is usually good numbers. So what was missing? What could they have done better? What one experiment can you add to support their thesis statement even more strongly? Okay, so we're looking at it from a critical review point of view. We have to see that they have planned out their paper with their thesis statement, with their data that supports their thesis statement, and their summary that supports their thesis statement. It should all be congruent. Okay, there can be some extra data in there too, that's fine. But why would you put extra data in there if it doesn't go to all the little points on your thesis statement? So I want to see that kind of thing in these, okay? So we can start doing those next Thursday, not this Thursday, but next Thursday. First thing you do is go get a good paper and email it to me because I have to read it to make sure that you're.
Are you going to prefer on papers?
No, I just want to read it ahead of time so that I can make notes, figure out what I want to catch you on. So, and what's missing. So you should all have the template, and I also emailed the rubric. So you can see what I'm going to be counting points for. So, okay, let's get back to today is part 1, nanocellulose. So I didn't know a whole bunch about nanocellulose until I actually started looking for this thing, and I noticed it wasn't in the book, but I thought it would be something I could do. Plus, I want to do the nanoenergetics as an extra special topic. It's not in the book. But the thing about nanocellulose is it's really coming along really well. That it can do a lot of things, and they're using it in a lot of things like scaffolding and wound control, and it's biodegradable. It's made from natural products, and so that's where we want to get in there. So when we're talking about nanocellulose, we have to think about what does nano mean? Well, we know what nano means. In the case of nanocellulose, we actually have 2 forms. We have a nanofiber, we have nanocrystals. Okay, and I'll show you where they both come from. What's the difference? But in every plant fiber, there's these cell walls that are around there, and they have these fibril materials in there that if you keep breaking them down, you're going to get down to these nanofibers that are all made out of sugars. So they're technically polysaccharides. Okay, different kinds of sugars make different kind of fibers, and you can actually have a bunch of different things there. But for the most part, we're looking at things derived from natural sources and a variety of natural sources, or synthesized by fungus and or bacteria. Okay, because they're going to be real precise about how they build it. Okay, so in contrast, nanocrystals, while they are made from the exact same material, they're actually smaller, highly crystalline sections of our nanofibers. Okay, our nanofibers have crystalline zones, but then they're connected by a less ordered section. And when you make nanocrystals, you cut those less ordered sections and keep the crystalline part by itself. Okay, but it's still made from the same kind of fibril stuff, but the nanocrystals, which are usually depicted as these double-pointed things, aggregate differently than the nanofibers. The nanofibers have a much longer persistence length, but the nanocrystals have more rigidity. Okay, so there's also different ways to make them. Most of the time when you do a chemical treatment on it, most of the time it's usually a acid-based hydrolysis. That's going to break up all the non-crystalline sections and give you just those nanocrystals, and they have smaller aspect ratios than the fibers. If you took your cellulose nanofibrils and put them in an acid treatment, you would actually get that here. Okay, but most of the time when you do the fibrils, they actually want the longer persistence length. So they go through typically a mechanical processing step to get the fibers to be broken apart and out of little bundles. And so they have this much longer length to them. Okay. So I'm going to start with this comprehensive review of nanocellulose crystals and nanocellulose fibers. And this is their front page picture that they have. And they're going from bamboo to get all of the other biological things out of here, the hemicellulose, the lignin, the cell walls, and everything like that. And then isolate just the fibers or isolate the crystals. So they get either the crystals here or the fibers here by different little things, and they're getting them all from a naturally sourced. No, these are going to be a bunch of different places.
Isn't it like an optical fiber, like the buffer and cladding and core?
Well, I mean, it's just the number of different layers holding the crystalline fibrils. We have an amorphous side on the outside of it. Then we have crystalline cellulose, and then we have the lignin in the middle. So they're just, each fiber has several components to it. None of them are just 100% cellulose. And so you actually have to purify off all of those things that aren't your cellulose or aren't going to be your fiber. Okay, so here's a bunch of different sources for that. We can do it from leaves, grass, shoot, oak husk, wheat straw, corn straw. So anything that has basically lignin and or cellulose in it, you can turn it into a nanofiber or a nanocrystal just by processing. You can even use paper waste. Cellulose, I mean, paper is like 90% cellulose. It's got some binders and stuff in there. If it's shiny, it has clay on the top. But you can use that and use this to make nanocellulose. You can even extract it from freshly harvested materials like bamboo and a lot of people like to use hemp or sage grass, and tall grasses that grow very fast. Okay. So in the first part of this, once you get your fibers isolated, you have to purify them. And so there's several steps in this. One is the bleaching step. The bleaching step gets all the minerals, all of the salts, and a lot of color out of your system. And if you'll look here, most of the time, they're actually using chlorate, sodium chlorate. Okay, sodium hypochlorite, which is HClO, is bleach. So it's a stronger oxidizer than bleach and sodium chloride. And then they either have an acid or a weak acid as their buffer. And all of these different systems can get very pure materials. It takes longer time depending on how thick your outer amorphous phospholipid is on your nanofibers. So it takes longer to permeate in and dissolve away. So some of the different materials take longer than others to get out of the system. One of the good ones here is wood pulp, because there's a lot of excess wood pulp from the making of timber. So, and it's actually pretty intermediate as far as time and temperature. Okay. So the next part is the alkali treatment. The alkali treatment helps get the fibers to spread apart, and it kind of gets them ready to do that final step, either the acid treatment for crystallization for the crystals or a mechanical treatment. And all of these use mostly sodium hydroxide right here, fairly concentrated solutions on a lot of them. And again, time and temperature depends on what kind of stuff you have. Again, wood pulp is not on there, but waste disposal cup, which is most consumer recycles, are very reasonable times and temperatures to do that separation. And notice they have also equipment to help. Mechanical stirring just gives it a little bit of shear. It's a low shear system. A digester typically does a high shear, as a high shear mixing. And this one at reflux is like, that's a lot of base heating at 120 degrees. Oh, yeah. So, okay. So let's take a look at really the difference here. So you make polymer nanocrystals from polymer nanofibers. Okay. So the first thing you want to do is you want to isolate the polymer nanofibers right here. And then there's these disorder amorphous regions and these highly crystalline regions, like 95% crystalline area here. Okay. So then if you take an acid and flip off these regions here, it actually is going to dissolve a little bit away of the crystalline machine as well, but it's going to leave that. And there's even another type in one of the books, one of the last references I have here, where they actually try to cleave it and then have the little fibrils hanging off the ends. Why would you want to do that?
Interaction.
Exactly. You can probably, because if the crystal's this big and have fibrils sticking out, it's almost like its own composite. It can maybe get into the matrix better and stay in the matrix better. So, but it's all a question of, do I want to set this in acid for an hour or two to get these, or do I want the fibrils? And it's depending on your use case too. Okay. So in this case here, we're looking at the preparation of the nanocrystals by using various different things. So we have sulfuric and hydrochloric acid are the first two. And then they dry the method using freeze drying. Okay. So what's the benefit of using freeze drying if you just chopped up your little crystals here? So if you freeze dry or lyophilize, what you're going to get is instead of if you just dried it, the crystals would start to aggregate and form bundles and form mats. So by lyophilizing it, you're going to get them as dispersed as possible, and then as long as you don't mechanically compress it, if you infuse a resin in there, they're going to stay dispersed. So lyophilization is used a lot in these. Okay, and they were able to get, rod-like structures, some better than others. These are a little aggregated right here, but they were able to get some structures there. Now, changing the acid to phosphoric acid, it actually didn't seem to work as well, but they also dried it by freeze drying. Okay, so this is it's like they probably weren't as dispersed as they should have been when they started freeze drying. But notice they're a little bit longer than those other ones. These are still, this is 100 nanometer, that's 200 nanometer. So the different acids give different lengths sometimes. So in this one right here, we're going to formic acid and malic acid. And the images aren't quite as good here. This looks like it's probably aggregated quite a bit, but these look pretty good about being separated materials. Again, this is freeze-dried. So this is the structure I would expect to see in a freeze-dried sample, where it's nice and dispersed so you can infuse the resin into it more. Then, okay. Oh, sorry, I already used that image. Okay, so how do you prepare these carbon nanofibers with our system? That was, the acid process is just making the nanocrystals. In the nanofibers, we don't want to break. We want to have those little flexible linkages that give us our flexibility in our long fibers and give us our long length here. So we can do high pressure homogenization, and that's typically done where you pump a fluid through a small orifice and then you apply back pressure to it. So the shear that's going through the product, it's almost like you're pushing on a ball. You're pumping up against the ball, and the shear of it going past there. It's used for pasteurization. In milk, it makes emulsions really stable. So that's high pressure homogenization. Microfluidization is a little bit different. Microfluidization is where you have it pumping, but you're having a pump and it goes through two holes and then they come back on each other. And so it's still a high shear point where you're going through the two small holes, but it is not scalable, as you will. High pressure homogenization is scalable. They have million-gallon ones. Sorry. Potential spam. You want to answer it? All right. So microfluidization is great for in the lab. You can make like 10 grams of it in a couple days in the lab, but it's really not good for that. Ball milling is really industrial process. I once saw a ball mill that was 40 feet long and 20 feet diameter. And so it was a continuous process. It just had these little things that just kept going. Had this cup at the end and catch the material, the ball material, and the powder just came out. Grinding, which is what you'd expect to have, that's grinding usually like a coffee grinder or something like that. It's kind of a mastication type process. Then there's cryo crushing. Cryo crushing is where you get wetted fibers and freeze them with nitrogen. The benefit of that is that when water freezes, it expands. So when it expands, it helps tear through the cell walls. It helps liberate the fibers. So that actually has a good one. The next one I like is, go ahead.
For the ball milling, so we are actually making them in the powder. Aren't we in the process of using them in fibers?
Okay, this is to get to the fiber. So they have to break all the outer husks off and all that other thing. And, because when you saw them, those bundles and bundles and bundles makes an actual plant fiber. We're breaking those bundles apart. We're breaking off the outer case to get to the fiber. So there's a lot of physical processing to get those materials that are not cellulose, lignin, and all these other sugars, salts, things that could be. So we're just trying to get to the fiber. We haven't even got to the fiber yet. We're still trying to get to the fiber. Okay. Steam explosion is a great one. I love the name. I would have called it something else. But, so in steam explosion, what you do is you put your stuff into an autoclave at 180 degrees, and you just cook it down for a long time. And then you get the guy with only one hand on the lap to go and just open it and let it go all at once. So I don't know if it's the guy with one hand, but it does not sound safe to me to do that, but it's like your it's called Instapot. You just go. So anyway, so that blows the fibers apart because the water that gets entrained into the fibers is expanding at a massive rate because of the steam. It's to 200 times the volume. So that works really well. And of course, sonication works really well. Again, only lab scale for small stuff. Okay. So when they compare all these different types here, the first two here we're going to compare are the ball milling and the grinding. So you can get different things like here they got straight fibers and here they got a web-like structure. But look how they dry. They did oven dry. So you have your material that you just ball milled in a liquid, and then you just let it dry. And of course, it's going to form a mat. And so they got a very mat-like structure. Now, in this one right here, they did grinding, and they got, it was only 250 RPM for 24 minutes. I thought it was hours. But anyway, they got nice fibers, but they did supercritical drying. So supercritical drying, as you may know, uses like CO2 or another gas where you can get to a triple point. You can have it hot and it will go from liquid phase to gas phase instantly, and therefore not having aggregation. So the lack of aggregation in the long fibers here is probably due to the drying process more than the actual physical massification process of grinding. Okay, and then let's do high pressure against ultrasonication. In high pressure microfluidization, and they're shooting it through these, they're pumping it through these small orifices and trying to get that differential pressure to blow them apart. They freeze dry them and got spherical-like structures. So maybe there was a little too much shear in that system, or maybe those are aggregates of the crystals. They're not very long. But they did do freeze drying, so they were at least dispersed quite well. In the case here, they had a web-like structure, but they also did freeze drying. And notice this is the web-like structure they're proposing. Why do you think they got that web-like structure instead of the other thing that is on the other side? They did freeze drying too. First one. Yeah, this one compared with that one. Okay, a supercritical dried, but this is freeze dried. Okay, so this was free. Oh, okay. This is the first one, it's freeze dried. Okay. So there's a reason it has this structure. When you freeze dry something, you have to have a solvent, and it could be water, but a lot of times you'll use something more like T-butanol, because T-butanol does not expand when it freeze dries, so it doesn't break your structure. But what happens is, as the crystals grow, the crystals are now solid, and whatever's in solution gets forced to those interfaces between the ice crystals. So these are where the ice crystals were before they were sublimated out by freeze drying. So you do see this kind of structure when you freeze dry, and it has everything to do with the crystals growing. That's why in one of those papers we saw, they did a biaxial growing of their crystals by only chilling down part of it and letting it grow radially out from that. And when they do that, they get order. Here we have a complete disorder in our system. Okay. All right, and then this is high pressure homogenization with freeze drying, and they get the web-like structure. But they're really long, nice fibers. So those are the primary ways to make nanofibers. Okay. And there's probably a lot more, but these are the ones that were in the view. Okay. Now this is where we have two more. We have the cryo crushing, and then sonication gave little tiny fiber mats. Okay. This really is not very big. It's this mat on a substrate here. So it gave a mat-like structure. This one, on the other hand, is the, not cryo grinding, but the mechanical steam explosion process and then air dried. So steam explosion process looks like it makes a really good matty structure, but there's also, it seems like they have, this is like maybe a bundle, and these have fully broken apart. So it looks like that was maybe a fibril instead of just a fiber. Okay. So then, once you get to that process, there's post-processing. And in post-processing, there's a couple different things you can do. Centrifugation. So that gets all your solids down, and what the benefit of that is, then you pour off your water, then you add more water to dilute out what salts or what other things you have. And so you can do that process many times. Dialysis process, which is where, everybody know what dialysis is? Okay, so the dialysis process is really used to get out like metals and small things like that. And then the sonication process is, of course, a really good one for dispersing white. Then drying, right here, evaporation of solvent is probably the least practical, but most practical for industrial purposes. However, it means you're going to have to try so hard to get them back into solution. So we want to avoid that. Drying by lyophilization or freeze drying, that's the next one here. That's going to give you nice dispersed low density materials, and you can control the crystal size by your freezing. There. Drying using supercritical state or spray drying. Spray drying is actually really cool. SWRI down in San Antonio has a huge spray drying facility. They have like 20 different kinds of spray drying that they can use, and it does micro encapsulation, nano encapsulation. In spray drying, you're literally taking a solution of it and blowing it up or down into a heated area and then having it evaporate before your solid touches the ground. And your solid is dry when it hits the ground, and then you just sweep it up. That's your material, and it makes a nicely dispersed material. Yes.
Is it really worth to carry on these long procedures to get the fibers? Like, would they be a burden on financially?
Well, the starting material is very cheap.
Yeah.
And if you're using mostly water as your processing aid, that's cheap. So it's not like carbon nanotubes and having to sonicate them and toluene and exotic solvents. So I think that there is a financial benefit to this, especially when you start looking at some of the applications. It is plausible, and I actually have one paper on the last one is on production and costs. So
Do you actually, industrial scale or large scale, is the sanitation process preferable or it's applicable?
no,
There's
no, because it's hard to get. See, if you have just a little sample and a little tip, you can get like 500 watts in that little section. If you're doing a flow process, you have to have the entire flow process under sonication. And once you start getting into 500 and 1,000 watt sonicator modules, those are like $5,000. So
try to disperse the chassis, it's about 1 hour maybe, and then it's just warm the water solution.
Right. The other problem with sonication is it's a batch process. When these go to really high scale, and there's like I have a slide with like 7 companies who are actually making these commercially at commercial scale. I believe that they would want to use a flow process. So the high shear homogenization would be better. The lyophilization is a batch type process. Drying is a batch type process. Ball mill can be continuous process. So they're going to try to go for as many continuous processes as possible to make it economically viable.
Theoretically, you did just the cost analysis of the complete LCA.
Well, not to hold LCA. It's more like, this is where these are the products where the nano composite is worth the extra money. So the value add is there. Okay, so and then this is one with this where they have spray drying here, and the one that's spray drying is right here at the end. And so it's kind of really cool that it gives this, because imagine it's just drifting down like snowflakes. In fact, the room that I was writing a proposal with them 2 years ago, the room is like 40 feet tall, and the sprayer is in the middle of the room. And they just line the whole floor with plastic, walk out.
The heating elements like on the side.
No, it's ambient temperature. Comes out in a heated solution to help it rapidly go. And then they use that room for air, but they have another room that's smaller, it's an explosion curve. So they can use other solvents. But it's really a cool process. And so this is a comparison of evaporation, freeze drying, evaporation, freeze drying, supercritical drying, and spray drying. Again, spray drying is very economical, especially if you're using water, because it doesn't have to be explosion proof. Okay, so let's talk about some of the things, ways to characterize these things. Now, it starts getting really, you can get, depending on what you want to do, you have to analyze them differently. Obviously, you can do dynamic light scattering if you have nanocrystals. Why won't dynamic light scattering work well on fibrils? Well, they're disordered, but they also, the signal in the line of the laser and the signal orthogonal to the laser are different. So you're going to get this, you're not going to get the actual volumetric size of the particle. But the crystals are much smaller, they have much smaller aspect ratio, and then so you can actually see that they're rotating around faster. And so that kind of work. Zeta potential, if you're going to use it for water purification, you want to know zeta potential. And turbidity, which is interesting. Then there's shear by refrigerants, and and this book, this article went on for like 10 more pages on different analytics. So we've seen a lot of things. You know, SEM is one of our go-tos, and X-ray crystal diffraction is one of ours. But I wanted to bring up a couple of these to show. Huh?
So the characterization in which sense, the chemical characterization or physical, like the turbidity just determine how much like base you have, like water turbidity.
Well, the turbidity gives us two things. It gives you a number of smaller soluble materials, and then whether or not you have what the settling rate is. So that tells you have either one fibrils settle slower than pixels. You can see here. But let me go through a couple of these, and I want to show you just a few of them because it really went on for pages. So this first one right here is looking at the light scatter. And so when you have different little sets, you can see really nice small things here, and then this one actually had 3 different peaks in that same sample. So we have one thing that's nano, that's actually 5 nanometers here, and then one thing that's just above here. So this is like an aggregate of these particles here. And then this is obviously probably not even broken down, but this sample here, it has no small part, it's completely aggregate. So we can see that from light scattering, assuming you have a crystals. And these are crystals here showing that we have a large fraction and small fraction. So that's one cool way to look at light scattering, and it's a very fast technique. And if you're in water, it's a really good way to do it. One of the other things they do here is this is zeta potential. So in zeta potential, what we're doing is we're looking for the potential generated as you flow across a solid. I don't know photosynthesis or something. But it's the interaction with a mobile phase, and there's a potential generated. So if you have a high zeta potential, you're going to get better separation than something with a low zeta potential. I forgot the actual thing there. Oh well, I published that 20 years ago. I don't remember. Actually got a patent where we use zeta potential to measure the efficiency of our resin recovery. So, and then turbidity here. Turbidity gives us an idea about large and small particles. Okay, large particles will scatter light. After your particle gets smaller than about 1/6 of the wavelength of light, it no longer scatters. So you can actually say that this right here, there's lots of large particles in here. As your solutions get less and less turbid or more of transmissive, then you have to hit it with like a laser to watch it scatter. But that lower color is telling you have less large particles scattering. So turbidity is a really good measure of how far along your process is going. And then they have what's called strong acid calibration, not calibration, strong acid hydrolysis coulometric curve. And so what they have here is they start out with an acidic sample here, and they measure the conductivity. And then as they take away the protonated species along the nanocrystals, it goes until you have a breakpoint, and then conductivity goes back up because now you're taking the protons from those. And from that, you can get an average hydroxyl number, which gives you an average of their size. And then they also have another one that's very similar. It's called the weak acid one, where it gives you the same kind of curve right here. And so the strong acid will give you this part of the curve. The weak acid gives you this part of the curve. And then this is completely based. There's only hydroxide. And our conductivity has changed going through those different regimes. And so you can get the apex of this right here is your strong acid number. The apex of this is your weak acid number. And this is fully hydroxyl. So that's one analysis we've never seen before. And it goes for the fact that cellulose has, or all of these sugars have lots of hydroxyls on the outside surface. That which lends to their crystallinity because they can crystallize with hydrogen bonding. And it lends itself to these other analysis techniques we haven't used up to now. Just missed that. Okay.
I think his battery is also low, sir.
Hmm?
The battery.
Oh, I didn't plug in. Oh, thank you. I keep forgetting to plug that in sometimes. All right, so this is going to be a little harder to see. So this is where I stopped writing because there are so many techniques here. They can do the ones where you look at the dispersion quality and you have turbidity, the zeta potential, and dynamic measurement. But they also have shear birefringence. In a shear birefringence, you have a microscope set up with cross-polarized light, and you flow your material through under the microscope, and you're looking for any transmission of light. When they're cross-polarized, it should be fully dark, but if there is a order in the flow, if there's order in the flow, you get birefringence and you get light. So you can look for dispersion, good dispersion with that. These are the surface charge, which is also, zeta potential titrations with the different types. You can get surface charge on your fibers. Elemental analysis, traditional carbon, hydrogen, nitrogen analysis. But then there's also XDS and EDX that you can measure exact kinds of elements there. Like what's your nitrogen content? That's actually what a lot of people like to see because lignin has the nitrogen in it, and so they really try to get rid of most of lignin, just have the cellulose, the pure cellulose. But then you can also look at the solid state properties of XRD, Raman, and NMR. And it's funny, there's like table after table of all the shifts with all the different carbon NMR. Then, of course, there's surface modifications you can follow by FTIR, NMR, and then radiological behavior that we can look at with rheometers or viscometers or shear methods like that. And so that also tells you that whether or not they're entangling or whether they're dispersed. All right, so then started looking at some of the potential applications. Okay, now this is where you have to go for your business case, right? So one of the things that is here is the paper industries. Okay, paper's come a long way. Paper's got a lot of stuff going for it, but adding nanofibrils to your system makes the paper stronger, makes it cut resistant, makes it usable in everything. Structural industries. This is like looking at composites, making composites for different structures that were the carbon the nanocrystals actually help toughen epoxy. Food packaging industry. Why would food packaging industry buy? And it's biodegradable. Biodegradable, so that you can have your throwaway meal package, be totally dissolved away by all the microbes. And so that's a great thing. Conductive ink, of course, if you look at the conductive material, what you're using the nanocrystal for is as a binder and or rheology modifier. You want inks to be laid on in a certain way. If you're doing silk screening, you need to have small particles and high viscosity. If you're doing inkjet, you have to have no particles and low viscosity. So the modifiers are really important. Printed electronics, if you already have a conductive ink, you can do that. Oil and gas fill applications. Right now, they're using a bunch of different fracking fluids that go into there, and of course, those are showing up in bad places. Turns out they can use nanocellulose as a rheology modifier, and they can use it as a fracking fluid, which is 100% biodegradable. You pump it up with water, pump up the nanocrystalline fibrils, and get the viscosity up high enough to do the cracking of the pneumatic cracking of the underground oil shales so they can extract them. On the medical field, I'm going to talk several things about the medical field and wastewater treatment. This has such a high surface area and all these hydroxyls on it, you can use it to bind metals and dyes out of the water. So it's used a lot for water purification. Okay. So those are the potential applications for that. So now I want to get to a specific paper talking about one particular purpose here. And this one, we're going to talk about fiber used for 3D printing bioapplication. Why would you want to 3D print something for a bioapplication?
Because it will link between the
Yes.
the layers. The layers will stick it to it.
Right, and skin scaffold, cellular scaffolds, whole bunch of things that can be done. So in this case here, they want to do 3D printed structures to make a scaffold. And so they kind of made their own polyurethane that was in water. And then they got it to a certain point, and then they added the nanocellulose to the system. Now, what they're doing for this is they're actually trying to get our nanocellulose fibers here to act as a structural support for the very flexible polyurethane. Okay, and so when you do it first, you're going to have this flexible polyurethane, but this is your rigid component. And that's the component. Not only is it a rigid component, but it can also react because it has all those hydroxyls. It can react with the polyurethane as well and become an integral part of the composite. Okay, and so they tried a couple different ways to do this. They tried just shaking and sonicating, and they saw that they got compact films. It really wasn't dispersed very well. It didn't make a very good dispersion. We kind of expected that with the shaking, but sonication usually does a pretty good job. So then they actually made the polymer in situ. They already had a solution of finely dispersed polymers, the nanofibers, and then they added the components in there and polymerized it, and they did okay. And then they added extra triethylamine as a neutralizer. So what that's doing is that's taking away some of the acidity of the nanofibers. And look at the rheology difference between having a neutral fiber and having a slightly acidic fiber. You're having a neutralized fiber that gives a gel-like appearance, which gives it a nice shelf life. So now, what's the other benefit of having this like this here? If we're going to 3D print, high viscosity makes it easy to print. You don't have to heat it up, but also it doesn't drip. The high viscosity also makes it more precise and makes you're assuming it shear thins a little bit to get through the nozzle, but then it immediately sets up again. That's
good, I think, extrudability.
right. And so imagine that you're shear thinning as you're going through your nozzle, and as soon as it leaves, you also want it to kind of like seize up and get high viscosity right away as well. So that was kind of their process for doing that. And they were able to go through and analyze these, and they looked at their, TGA, and of course, it's going to be different from that. But they also looked for their melt and decomposition temperature after printing. So that means they have a use temperature here. It's pretty good. They looked at heat flow, which is going to give us the not reality. This is like a DSC showing that we don't have any big melts or recrystallizations going on. And we saw decreased percent elongation, which we know that happens when you put in an analogy. So their properties are good enough to use for their 3D printed scaffolds. So then they go ahead and looked at seeing if they were still well dispersed. And after drying, they still had little teeny pieces all over the place. And so they said that they had still good dispersion of their material in this ink. Okay, in this. So what they think is happening, why there are those little sphere-like things here, is that the polyurethanes actually growing a nanocrystal off of the fibers, off of the hydroxyls of the fibers. Okay, I've seen this behavior in cyanates, cyanate esters. Those do this kind of behavior. Well, they'll grow out in spherical nature if they're constrained. I have not seen it in polyurethane, especially a really plasticky polyurethane. But they say because the reactive groups on the polyurethane can react with the hydroxides on the fiber itself, you can get one end and then the other end, and then so that constrains the entire length in between there from being a linear polymer to being a polymer nodule. And then of course, because has the similar intermolecular forces, it will crystallize and form it. So this wasn't necessarily a bad thing or a good thing, but it was still something they did notice. And then they build their scaffolds. Okay. So when they build their scaffolds, they look like this. They're trying to get something that can be fused and as to put cells on. They're trying to get a cell scaffold here. And when they first made it, it looked like this, and it was printed, and so it was still had some solution in it, a little bit of water in it, because it had a flow. And so it was going to shrink. Okay. Now, when they had it without drying it, it stays together and doesn't fall apart. But when it dries, it actually shrinks significantly. So see, this is almost an inch wide, and this is the other printed one right here. They shrink down to about half their size. Now, in this case here, they actually did freeze fracture to look at the internal structure to see what the printing layers were and to see how strong it was. Again, it's a cell culture. It doesn't have to be mechanically strong. It just has to be the right surface energy for the system and be able to infiltrate from those things. Okay. So then they did the same thing, but instead of using the cellulose nanofibers in there, they tried to use PEO as the other thing, saying, oh, it's not going to add anything to the structure. And what they saw was they were able to do the same printing, got similar results here, but it was much more fragile than the one with the carbon nanofiber. Sorry. Cellulose nanofibers in there. Cellulose nanofibers really did help the structure and helped with that. They didn't actually do any cell culturing on there, but they did. Huh?
What's
Polyethylene oxide. It's one of those polymers. Okay.
Did they try freeze drying?
Not in this one, because they really don't need it dry. They can actually have it soaked in water the whole time, because it's a scaffold. So, but they did dry them to do the freeze fracture to look at the internal structures. And then from those freeze fractures, they actually looked at the internal structure of it here. And let me get this straight. Let's see. A and B are the carbon nanofiber structures. And then, and they're from different just parts, right? And so if you zoom in on one of the freeze fractures of this, they are saying that these little things right here are their cellulose nanofibers. And they're adding to the structure of the material. And those are some of the other, let's see, or stacking, studying stacking fibers, and then seeing the presence of nanofibers indicates where the freeze.
What do the scaffolds do?
Scaffolds act as a place for cells to grow. So it has a surface amenable to their their outer walls, and so it doesn't irritate them, and they're porous, so you can get nutrients in and out. And by controlling the structure, you can actually get cells to grow in certain patterns. You can grow nerve cells, like if you have conducting fibers, they're all going in one direction, the nerve cells will grow along the axis. So, but what they saw was that as they dried, they saw this shrinking. When you have the PEO in there, the PEO, polyethylene oxide, does not evaporate as with the water within the carbon nanocomposite. So the black one is with PEO. And so once they let all the water dry out of it, they got to this remaining loss about 25% of its weight. The carbon nanofiber one loses less water weight. And then if you take the PEO out of the system, you actually have no loss of weight in polyurethane. So, but look at the shrinkage here. We have, this is an inch right here, down to a little bit over half an inch, under half an inch to, over half an inch to under half an inch. So they see shrinking coming. There are these two. So they do see a lot of shrinking in their system when they remove the water.
So what's PDS?
PDS?
PDS, you said that's what they so
PDS. Oh, not synthetic blood serum. I don't want to hurt them, sorry.
Sure, it's a buffer mixture.
Yeah, that makes sense. A buffered artificial saline. And then they looked at whether or not it actually grew cells on there, and they used fluorescent spectroscopy on here to look for cell growth. What they saw was that their cell viability continued to rise over time. Notice the PEO was not as good as these are about the same here, but the carbon, cellulose nanofibers made a more cell-worthy growing substrate. So they were successful in proving their thesis. Probably took a year to do all that too. Okay. So now I want to switch gears a little and talk a little bit about another way of doing these composites. And these are in hydrogels. Hydrogels are a little bit different. We haven't talked about that as a composite material. We're going to talk about it. And again, this is going from how you get it from the wood fibers to breaking the cell walls to getting the fibrils to breaking the fibrils to getting the nano materials. And if you chemical treat it, you get the crystals, and if you don't, you get fibrils. Now, these are crystals that this one's talking about. Right here, you can see they have neat aspect ratio. And this is done with an AFM. So it's a tapping mechanical technique. So hydrogels are a little bit different than what we've been doing here because they're swollen with a solid. Okay. So in the case of this, you can make them a couple different ways. The first way to do it is you have your stuff and you cross-link it either chemically or using hydrogen bonding. And so that'll use it. Usually when you cross-link it, it's usually a covalent bond. Or you can use heating. In the case of collagen and stuff like that, the hydrogen bonds break down above 70 degrees C, and therefore it gets free. And then as soon as you lower the temperature, it will re-aggregate. Then there's self-assembly, especially if you have long things like peptides or proteins, those are self-assembly. And then there's composites. And in this one here, you're actually using a bidentate metal ion to cross-link as an ion cross-link. So it's like I can bond twice. I'm going to take one on this side, one on this side, and cross-link that way. So it works with bidentate and tridentate ions. Calcium and aluminum are two most common used.
The polymer have to have
The polymer should have a positive, should have a negative formal charge. So yeah, preferably evenly distributed along the chain. So the hydrogels are used specifically because of their biocompatibility. Because when you're getting the polymers you're making these gels out of actually come from biological systems. So you can get the alginate-based system, which is also biodegradable. Chitin, chitosan, and chitin come from bug exoskeletons and a variety of things. Lignin is pretty good at, it's one of the other fibers you get from just wood. Gelatin is a biocompatible one, but it also has, it's usually now synthetically made, or it comes as an extract from chemical products. But they have different purposes here. So pH sensing, non-toxic deodorizing properties, cellular affinity, antioxidant, antifungal, heavy metal removal, biocompatibility, ease of use functionalization, tasteless, hydrophilic, biodegradable material, insoluble in water. But then we have their limitations. Things like most of them have low mechanical properties. Hydrogels typically have very poor because of their solvent swollen nature. But then you look at the application here, heavy metals and drug delivery. So we're doing two different things there. We're asking the aerogel, the hydrogel, to, in one case, suck things up, and in the other case, release things. But guess what? As long as you have some permeability and some diffusibility, you can do either one. And so it works in both cases with that. Now, the next thing that it says is wound care. I'm going to talk a lot about wound care, a little bit more about wound care in a minute. But there's the properties of hydrogels are actually really good for wound care. And with or without a nano component, they can even have nano silver in them for antibacterial agents or nanofibrils to give us structure. So a lot of these are the same with tissue engineering and or drug delivery and or wound care. So I think okay. So let's talk about the kind of physical attachments that happen in this. For the most common of the hydrogels, it's a chemical cross-link system. But that's not the only thing that can tie a hydrogel together. In this case here, we have a highly cross-linked system. But notice we have different little structures here. We have a dense formation, loops, dangling ends, and stuff like that. But we can also have our chemical cross-links, but then we can also have entanglements, or loops, or just crossover points that have enough electrostatic energy to hold that position. And all of these types of things happen in hydrogels, always. So you're always going to have them unless you have some kind of pre-ordering method to get it to go. Okay, so they are two things that we're going to look at here. We're going to look at a traditional bulk hydrogel. You can make it in a bucket. So basically, you do that either by bulk polymerization with or without the material that you want to infuse in it. For example, most baby diapers have a polymethacrylic hydrogel in them, and it's produced dry. And then they just put it in they package it in there, and so it'll suck up water. So it actually has a cross-link structure, but it's very hydrophilic. But it's done in bulk polymerization. Solution polymerization is more common, especially if you have the solvent that you want to be your structure in your hydrogel. A lot of times with water. But for injectable hydrogels, you actually needed to do a couple more things. You needed to be responsive to how to get it in exactly where you want it. You need to get it through the needle. Then you need it to gel when you're done through the needle. So you need to be liquid processable and then gel when you get it where you want it. And so there's a couple different ways you can do that by either a chemical cross-linking in that, which is kind of pinky if you want to do that inside somebody's body. You might not want that. But you can also do it with self-assembly, hydrogen bonding, ion interactions, crystallization. But the cool one is photo-induced cross-linking. Basically, inject it, get a UVC light on it, and adjust. And then you have a slow drug release injectable material. Okay. So let's talk about that. how can we get that to gel after injection using external stem? So if we want to do the chemical cross-linking or the physical cross-linking, physical cross-linking would be just, it binds onto the calcium ions that's found in the body, whatever bound up there. But the cool thing is you can use pH. So you can have a high pH material or a low pH material. When it gets to the body, it's going to go shift down to 7.8 and then gel. So you want something to be out just barely outside of that range for the gel that hits that pH. Temperature, you can keep the material cold and it gels when it's hot, or keep the material hot and it gels when it's cold. Electric or magnetic field. Just put them in an MRI and watch their arm explode. Or UV light. So they can as long as it's close enough to the surface of the skin that all the UV isn't absorbed, you can use UV light as well. Okay, so this is one of the ones that they did, where they had their carbon nanofibers and they modified their carbon nanofibers 2 different ways. Okay, in one component, they modified their hydrazine functionalized hyaluronic acid. And hyaluronic acid is actually a different, it's not actually cellulose, it's another large sugar. And so they modified it so it had a hydrazine unit which reacts really rapidly with these aldehyde units. And so they did that and mixed in some of their drug mixture here. Then they had the modified hyaluronic acid plus the carbon nano. They were both charged for the same thing. They both had functionality of that aldehyde. And notice their injector has 2 different things. It's a chemical cross-link system. And soon as those these right here, they're going to react and add across the double bond and extrude water. And so they're actually going to make it. And so they can get this nice cross-link mask that has the different elements that they want to slowly release into their system. But why are they using carbon nano, the cellulose nanofibers? Turns out the hyaluronic acid by itself is not very structurally stable. It would be very squishy. They're just using it for extra rigidity to hold the whole thing in place. So this is actually giving it the structure. This is giving us our chemical cross-links. But it still is better to have the cellulose nano. Okay. So where are we? Oh, okay. We're almost there. Okay, so I just want to look at some of these different materials and look at how they did it. With this alginate they used a magnetized cellulose nano crystal, which means they modified the surface with metal salt. So then they were able to freeze dry, and then they could use it for drug delivery. They used PEG as a material, and then they imperial modified that. So that is a furan. It's a hydrocarbon. Sorry, it's a heterocycle that can do an addition reaction. Solution polymerization for biomedical. Aldehyde modification. So that's the hyaluronic acid with the modifier. So that gave us a covalent cross-linking for tissue engineering. Another aldehyde one, chemical cross-linking, tempo treated. Tempo is actually a free radical generator. And so that would be a free radical polymerization system. They would use that, and then they freeze dry it and use it for wound healing. Peroxidate oxidation, that is also usually generates anionic or polymerization. Alginate with honey gave us an ionic gelation, and then they do free radical in solution. And then they've also added different weight percents here, all the way up to 50 in some of these, but as low as 0.1 to get the structure they want. So there's a wide range of what to do here, and a lot of them are for biotissue and wound care. I know I have a slide on wound care here somewhere. Not this one. So in the drug release system, they have a couple different mechanisms that can happen by that. Three things can happen once you inject your thing with your drug in there. It can slowly be decomposed by the body itself. Okay, so you can have either enzymes or whatever go and start slowly breaking your hydrogel out. As it's eroding away, it's releasing the drug. You can have it by swelling. And by swelling, what you're doing is you're going to pull in body fluids in, and then that's going to allow it to diffuse out over time. So you'll have a diffusion process there, but the structure itself does not break down. And then there's deformation. In deformation, you're actually putting an external stimuli to either make it constrict or expand or change shape. And when it does that, it allows for the diffusion of the done. So they can do mechanical, ultrasound, or magnetic to get this to release. The swelling can be done, with changing pH, changing temperature, changing ionic strength, and then the last one is usually decomposes the whole thing as it goes. There's the slide. Gosh. And this will be my last slide. Okay, here are some of the benefits that we get from a hydrogel for wound care. Number one, it provides a moist environment. If you have your cells trying to grow and there's a large amount of scar tissue or dried scabby material, it doesn't grow as fast. So keeping those from forming and letting the cells grow as fast as they can is really good. Side infection protection. So especially if you treat your thing to resist E. coli or any gram-negative or gram-positive bacteria, you can get really good results from that. Blood and exudants absorb. So blood and the exudants is pus. So it's the clear bodily fluids that come out of it. It can act as an absorbent.
There are two, I think it's very important.
Yeah, that must be. Wound surface necrosis protection. So in the case of necrosis, that's where the part of that skin or whatever has actually died, and it is really susceptible to being, taken over by bacteria because it has no operating white blood cells. So it's very important. Inspiring the growth rate, again, keeping that surface smooth without a whole bunch of solids on it. Keeps it there. It's elastic and stretchable and non-toxic biocompatible, especially if you use a water-based hydrogel and you infuse it with a bunch of different things like nanosilver or nitric oxide. Nitric oxide actually leads in here as well. You can have a slow nitric oxide release, infuse it juices. Slowly permeates and gets out. So anyway, we're right at 3:15. So well, let's see what the next slide is. Well, that's a different purpose. So we'll stop right here, and then I will continue on Thursday. Our first talks will be next Thursday. So
it will be very two. 2 days, like.
Yeah, it'll take 2 days because we have seminars. We can't go all. And so find your paper by Thursday, please. So you'll have 7 days to, or at least, a few days for, you'll have 7 days to start getting your slides together. Okay. And with that, I will stop share and stop recording.